take that topic, by the way. Great.
Oh, okay,
I'm
cool.
totally in.
Yeah, what was crazy is like after I sent you that email, the WHO also issued a warning about antibiotic resistance. I was like,
Oh,
wow.
I'm totally in. The other one was that I kept looking for is using the ocean for electricity. Because I was like really when you showed me that the thing in class about it, like I was like, that's amazing. So I was looking at that too, but this is perfect.
Nice. All right, let's go ahead and get started. So it just hit me at the beginning of class that we have to get through the entire chapter 14 today. Because I assume you don't want to spend Thursday Thanksgiving with me. So
I said as long as you don't have to come next.
all right, so just a reminder, if you haven't taken the lab final, today is the last day to do it. And then also I got everyone's emails. I didn't respond to everybody, but I got it all set up, or it will be set up for the reactions. And so this is our last makeup session as well. So if there are any labs that you need to do, come show up today. Otherwise, if you've done the final, you have all your labs, you don't need to come to lab. But you can still come, like if you need to come see me for office hour reasons or just finish stuff up. So then I'll see you then. Or if you want to make up quizzes, that would be a good time. Question?
I'm just wondering on the lab final, is that with your partners or is it like an exam?
It's individual, but it's super easy what you have to do for the lab final.
I like that.
Yeah, it should be easy. Like I'm not anticipating any issues with that. And so don't forget, so obviously we have Thanksgiving, and then that puts us, so next week, Tuesday, that will be our last review for the final. And so I'll try to go through similar questions to your exam and answer anything else. And then, of course, Thursday will be the final. And so don't forget about your paper as well. So I've gotten, or just the summary, so journal article summary. So I've gotten some emails from people about topics. And so again, if you need me to access a journal article for you, I can do that as well. We can talk about topics. So that's something else that we can discuss either after class or whenever. And so I'll also put on the calendar, so December 2nd at 1 p.m., we'll have our guest speaker for extra credit. And that will be recorded. So if you can't make it on that Friday, you can watch it at home later and just send me a sentence or two about what you found interesting. And then also, I forgot other extra credits, so just tell me that you registered or are going to register or whatever your plan is. You're transferring, switching schools, graduating, whatever that is, or even if it's taking time off, just let me know and you'll get the extra credit. All right, so let's do thermochemistry. So what is thermochemistry? And so this is a branch of thermodynamics that deals with the evolution or absorption of energy, as in chemical processes. And so you got a flavor of that with your last lab. So you got to see how you would measure the evolution of heat or absorption of energy with your calorimeter. So you saw that process. And so what is energy? And so energy is defined as the capacity to do work, and that's either going to be potential energy, so stored in chemical bonds. So hopefully, right, you had some food this morning, and so within that food is all that potential energy. And then, of course, your body breaks that down, and it gets converted to kinetic energy, so you can move about your day. So kinetic energy, then, is energy associated with motion, and so that also includes, like, the movement of electrons as well, so that would be kinetic, so just like the flow of electricity is also considered kinetic energy. And so work, so if you've taken some physics, you're probably familiar with the definition of work. And so work is some sort of force acting over a distance. And so energy is related to work, and then that's force, again, over your distance. Sorry. And so we have our first law of thermodynamics. So the first law of thermodynamics is the conservation of energy. So just like matter cannot be created or destroyed, same thing with energy. So it's just converted from one form to the next. And so thermodynamics is the study of energy and its interconversions. And so the first law of thermodynamics is the law of conservation of energy. So this means the total amount of energy in the universe is constant. So we can't just create energy from nothing. And so it is conserved. And so therefore you can also never design a system that will continue to produce energy without a source of energy. And let's talk about, hopefully we have time. So there's a couple fun theories with this. So some scientists predict the heat death of the universe. I don't know how accurate this is, but some people have proposed, so of course, if energy is conserved, right, we can't create any. And so we always lose some to entropy. And so this is proposing we might achieve some state where we can't have any difference of energy anymore and everything is just entropy and chaos. And so this would eventually lead to the heat death of the universe. So basically there's no difference anymore in energy, and so there's no way to perform work. And so here it says that temperature differences or other processes may no longer be exploited to perform work. And so that would mean our entire universe will be in thermodynamic equilibrium. So who knows? Just a theory, but something to think about when you're, up at night. And then, so the other thing, so have you guys ever heard of a perpetual motion machine?
Yes.
Yes, so you know that that can't be done. So that's just a theory. And so again, this would violate the law of thermodynamics. So this is just a theory. So could we make a machine that you don't have to do anything to and could just run and run forever? And of course, this just violates the first and second law of thermodynamics, or both, so not possible. So some more definitions. And so the system is defined as the part of the universe that is being studied. So in our lab, right, that was just our little reaction vessel, or whatever was in that calorimeter. So that was our system. And then the surroundings is anything else. And of course, right, that's also why you had to measure that kcal, because you were trying to see, well, how good is our calorimeter at keeping everything separate from the surroundings? And obviously you did that. You accounted for kind of how tricky that is too. And so again, your surrounding is just everything else outside of your system. So in our case, right, it would have been our lab environment and everything else around it, the tabletop, and wherever heat can go. Let's put air too, since you're probably losing heat to the air. And so again, thermodynamics is the study of energy then that is exchanged between the system and the surroundings. So again, that's what you were measuring with your calorimeter. So is it getting hot? Is it getting cold when you do these reactions? Which way is energy flowing? And so we have two different terms, and we'll look at them more in detail. We can define reactions as either being exothermic, and so that means that the energy of the system is dropping, and if the system is dropping, the energy of the surroundings increase, and so this means it's going to feel hot to us. So it feels hot, those products are lower in energy than the starting material. That energy difference then gets released as heat, which you feel. And I believe some of your calorimeter reactions were exothermic. And so we also have endothermic reactions. Did we do dissolving like ammonium chloride in this class? Maybe not. So when you dissolve ammonium chloride, so this is what's in ice packs, like those instant cold packs. And so it's just water and then ammonium chloride, and then when you break that barrier, then you cause the ammonium chloride to be dissolved in that water, except dissolving ammonium chloride is an endothermic process, so it requires energy. And so that's why the cold pack feels cold to you, so your body is supplying the heat for the ammonium chloride to dissolve. And so endothermic, again, it's taking energy from your body to increase to the system, and so of course feels cold to us. And then your products would be at a higher energy though, since it took, again, the energy from your surroundings. All right, so let's look at some work here and how to do work. And so let's examine our piston here. So our piston can just do work going up and down here. And so we have the force that's applying. So force so pressure is related to force over area. So we didn't talk about that in here. And then so the work that it's doing, so we apply some force, it does a displacement, and therefore we can figure out how much work is being done. So we have our volume change, and so that's what you would be interested in, so your change in volume. So of course for this would just be your area of your piston times your height difference. And so this is what we're focusing on then. So pressure volume work is work caused by a volume change against an external pressure. So that could be blowing up a balloon too, so that would be work. So you're working against your atmospheric pressure. And so when a gas expands, your change in volume is positive, but the system is doing work on the surroundings, so your work for your gas is negative. So does that make sense? So you're like, the gas is having to work against the surroundings, so it's doing work, and so it is negative. And so as long as the external pressure is kept constant, and so that just means, again, you're blowing a balloon up against your constant 1 atm of pressure, so you can't be changing the pressure. That would mess up this equation. It wouldn't have this linear relationship like that. And so in this case, the work done is just equal to the negative pressure times your change in volume. And again, the system is doing work, and so if you're working, the system is working, that's a negative sign there. And then whatever answer you get here, you can convert to joules using this conversion factor. So it looks like the pressure here should be an atm times your volume, and then convert it to joules with that factor. So you want to be an atm. All right, so let's look at how the problem would go. So take a minute or so. So to inflate a balloon, you must do pressure volume work on the surroundings. So if you inflate a balloon from a volume of 0.1 liters to 1.85 liters against an external pressure of 1 atm, how much work is done in joules? So then we could just set up our equation. So work equals negative P delta V. So we're already in 1 ATM, so that's good. So I'll just plug in 1 there for pressure. And then what's our change in volume? Would you say 1 point?
0.15.
So
Or no, 0.85.
0.85, I think it's off. So minus 1, so like 1.75 for delta V. And then, so times it by -1. And then we get our answer in ATM liters, but then it wants it in joules. So then we can just convert to joules. So let's write this here. So now we're at negative 1.75 ATM liters. We want to convert to joules, so multiply this by 101.3. So do we get negative 177 for our work? I see at least 1 nod, 2 nods. Let's see, we have 3 sig figs, so negative 177 joules. So from here, you just multiply by your 101.3. So did you get to the negative 1.75? And then, so once you get there, you just have to use this conversion factor. And so as long as you're in ATM liters, and you can set that up, and I can work it out more explicitly too. So you're in ATM liters. We want to go to joules. So 1 ATM liters goes on bottom, and 101.3 joules on top. So any questions on this one? And so now here are some signed conventions too to help you with this chapter. So anytime we're talking about heat, that's going to be our little q here. And if we're talking about a system gaining thermal energy, that's going to be a positive sign. So that kind of makes sense. So gaining energy, positive. Anytime you're losing thermal energy, you should have a negative sign. And then, so now we have work done on the system versus work done by the system. And so, right, if your problem says that you're doing work, so the system is doing work, that's where we get that negative sign from, versus if it was deflating, so then, right, we'd have a negative change in volume, work would be done on the system, and that would give you a positive sign. And I always think about that too, of like if you're getting a massage, right, you're getting work done on you, that's a positive thing, so there's your positive sign. And then we'll look at our total change in energy. So again, if energy is flowing into the system, that's going to be a positive sign. Anytime energy is flowing out of the system, negative sign. And so now we'll look at a few different graphical ways to represent our exothermic process. And so here we're looking at this reaction of carbon plus oxygen gives us CO2. And so if we're looking at this, so we have our reactants. So we have energy on our y-axis here. And so our reactants are higher in energy. And so our products are lower than, so then our change in energy is negative. So this is telling us that it's an exothermic process since we're, again, losing energy. And so whatever energy we lost here, obviously the surroundings then gain that. So again, that's your hand feeling that hot exothermic reaction, and you're getting that same energy into your hand as was lost by the system. And so, of course, they just have opposite signs. And so similarly for an endothermic process, so now we're looking at the reverse reaction. And so instead of the reactants being higher, now we have the products higher in energy. There are carbon plus oxygen. Reactants are in the bottom. And so we go from reactants to products, their change in energy is positive. And so same thing, whatever energy the system absorbed, that means the surroundings lost that same energy. So energy negative from the surroundings. I'll just put again there, feels cold, so we remember. And so now we have, right, our energy exchange then. So energy is exchanged between the system and surroundings through heat and work. So again, Q is going to be your heat, whatever heat is being gained or lost. Work is whatever work is being either done by or on the system. And so Q and W are not state functions, and all this means is that their values are path dependent. And then, so this gives us our total energy then. So our total energy, either lost or gained by the system, is equal to Q plus W. And so now we're going to focus on enthalpy, which is what we calculated in our calorimeter. And so enthalpy change is just defined as heat evolved at a constant pressure. So again, in lab, right, we're always at 1 atm, so that upholds for this case. And so enthalpy H of a system is the sum of the internal energy of the system and the product of pressure and volume. And so, right, this is the same thing. So delta energy is basically equal to Q plus W, right? So this is your work here, and then energy, again, from your heat of the system. And so that means that at constant pressure then, so this goes away, and so we just get our delta heat of reaction is equal to Q at constant pressure. And so also note, so enthalpy is a state function, so it's not path dependent, and so that is useful, so not path dependent. So that's why we were able to kind of manipulate, right, our delta H values, and we could, in lab, right, we were interested in one reaction, and then we used 3 separate reactions to determine that, since it's a state function, so it didn't matter how we got there. And so usually delta H and delta E are similar in value, so the difference is largest for reactions that produce or use large quantities of gas. And so now this should hopefully remind you of lab. And so Hess's law is what we were doing in lab. So this involves relationships then between our delta enthalpies of our reaction. And so enthalpy of a reaction is always associated with a particular reaction. And so that basically means it's for that molar amount. So however many moles are in the reaction, it scales up accordingly, up and down. Again, you saw that in your lab. That's why you had to account for like how many moles of magnesium you use, all that. And so if the reaction is changed, then your delta H has to do that. And so we kind of saw that too. So if you have A plus B gives you C with a delta H, right, of negative 50 kilojoules or whatever. And we saw we could flip it, giving you C gives you A plus B, and then we flip the sign in that case. And so same thing, right, we could double it, we could half it. So if we wanted to half this reaction, so half A plus half B gives us half C, then you half the enthalpy to give you half of that. And so that makes it an extensive physical property, so it depends on the amount. And again, it just scales, so whatever your reaction is, that's when you know how many moles. So if this is 1 mole or 2 moles, 0.5 moles, it doesn't matter. Just scale your stoichiometry appropriately. And so here's just another example. So we can look at 1 mole of carbon plus 1 mole of oxygen gives us CO2. That has a delta H of negative 393.5 kilojoules. We could double everything. And so if we multiply everything times 2, then we have to multiply our delta H times 2. And then like we saw in lab, reverse the reaction, and then that flips the sign of delta H. All right, so now we have to figure out, well, how do we calculate a standard enthalpy change for a reaction? So that's what we were answering in lab, right? It was like, how do we get this information just from different methods? And so all this means, so first let's define, well, what the heck does this mean when we say calculate standard enthalpy change? And so it says here, any reaction can be written as the sum of formation reactions for the reactants and products. And so your standard enthalpy change just means, so let's say we have CO2. And so we could write, first of all, if you want to get the standard enthalpy change, it would be, let's say we could just break this up into its atoms and then magically push it together to give you this product. What would that be? So that'd be carbon plus oxygen gives you CO2. So that's at least what you're looking for. And so let's do another one just so we can kind of see, or if we were interested in benzene, so C6H6, that would look something like 6 carbons plus 6 hydrogen, or 3 equivalents of hydrogen, gives you benzene. And so now there's a couple of methods to get there. And so maybe you know the standard heat of formation for some of these components. And so this is what's commonly used to figure out your delta H of some reaction. And so you can look up in a standard table, so your book should have all this information, but you can either define it as the sum of all the products of your delta H minus your delta H heat of formation for your reactants. So that's one way to give it. And so our standard conditions then, and what this is found for, so your table, so your standard enthalpy of formation, delta HF, is just a standard state, and it's just state of the material at a defined set of conditions. And so this means we're going to be at 1 atm. And so same thing, so whatever your form then, so if you have whatever substance, whatever its form is, should be at 1 atm. So, that means oxygen is going to be a gas, bromine is going to be a liquid, something like that. And so usually we're at 25 degrees Celsius, and our concentration of solutions is 1 molar. And so your standard enthalpy change is just your enthalpy change when all reactants and products are in their standard states, versus the standard enthalpy of formation is the enthalpy change for the reaction forming 1 mole of pure compound from its constituent elements. And so delta HF for a pure element is always 0 kilojoules per mole, since it's already in its standard state. And so your book should have some table of enthalpies that looks like this. And so you can just see what it takes. So notice bromine as a liquid, that's going to be its standard state, right? Bromine's a liquid at our 25 degrees Celsius, 1 atm. So it has a delta heat of formation of 0 versus what it takes to get it to a gas form. So that has a heat of formation of 111.9. And so again, you could just kind of appreciate some of these values so we know where to look them up. And then obviously, whenever you're looking at the table, just watch the units. It should be given in kilojoules per mole, but if you start Googling things and asking the internet, you can find other tables with different units, so just be careful. All right, so now let's see, I'll probably have to scroll up and down. So use your standard enthalpies of formation then to determine our delta heat of our reaction, or change in enthalpy for this reaction. So I'll let people copy down the reaction. Can everyone see it? It's kind of low. And I'll try to scroll up on the table.